Welcome to Study Loop.
So we're told that the length of the magnetic region over which the magnetic field is active, delta x, is 50 centimeters. So putting this in SI units, we write this in meters. So it's 0.5 meters. The speed of the silver atom, v, is 525 meters per second. And the separation spin between the two spin components is 2 times delta z. There's two spin components, so it's 2 times delta z, which we're told is 1 millimeter, which is 0.001 meters. And then we also know that the mass of the silver atom is 0.1079 kilograms per mole, which of course a mole is using Avogadro's number of 6.022 times 10 to the 23 atoms per mole. So the z component of the associated spin magnetic moment, mu sub z, is equal to 2.00232 times the charge of electron divided by 2 times the mass of the electron times s sub z, the z component of the spin. So we're dealing with electrons, so this is plus or minus h bar over 2. So if we plugged that into our expression, the 2's are going to cancel, so this is equal to 1.00116. So we just add that first number multiplied by h bar times e over 2. But h bar times e over 2m is equal to Bohr's magneton, mu sub b. So this would just be the z component of the spin if we were just dealing with a hydrogen atom with one electron. That's what Bohr's magnetron comes from. It's equal to e h bar over 2. Which we could write the numerical value of that. So in SI units, Bohr's magneton is equal to 9.274 times 10 to the minus 24 joules per Tesla. So we can go ahead and substitute that in. So that's just E h bar over 2m, where m is the mass of the electron. So this gives us a value of mu sub z equal to 9.2 times 10 to the minus 24. Okay, so now we have a numerical value here for our z component of the associated spin magnetic moment. So the time required to transmit the magnetic field region is the next thing we need to calculate. So this time, t, of course, is just going to be our distance relationship. So time is going to be equal to distance divided by velocity, delta x over v. We said that delta x is 0.5 meters and v is 525 meters per second. So the time of 0.5 meters when at that speed is 0.952 times 10 to the minus 3, which is 0.952 milliseconds. You could write it either way. I'll write it into the minus 6. So now we can find the force that is required to deflect each spin component by that distance delta x. This is because the force that is required, F. Classically, this is just equal to mass acceleration. But the acceleration is 2 delta z over t squared. And we know t. we know that 2 times delta Z is 2 times 0.5 millimeters. So we've already written this out. Again, 2 delta Z, we said, is 0.001 meters. And we've just found T previously above. It's the 0.952 times 10 to the minus 3 seconds. And we said that the mass, so we know the mass, because this is silver, is going to be 0.1079. This is per mole for silver. And we divide this by, of course, number of atoms per mole. So this is 6.02 times 10 to the 20 per mole. So that's our value for the mass. So we'll abbreviate with little atoms per mole. ATM for okay. And then again multiplied by our 2 times delta Z by T squared. Okay, so this here gives us a value for our force of 0.98 times 10 to the minus 22 newtons. So now we have all of the necessary values to calculate our change in magnetic field as a function of Z. So this is dB dZ. Since dB dZ dB dZ equal to the force divided by mu sub Z over the force, and we know mu sub Z, so we plug these values in, and we find that dZ is equal to 21.3, and the units, of course, are per meter. Since the units of magnetic field are Tesla, units of Z are meter. We can box that in as our solution.